Yeah, thank you very much to you. Stored granulated blast furnace like grindability and reactivity. So it's not really a new topic, but sometimes in our FEhS Institute we are surprised how often old topics, old questions arose again, coming from slag producers, cement producers, grinding facilities, trading companies, and so on. Short overview. I will give some information on the background of the presentation of our investigation. I give an overview what we did in the past. Of course, I will inform on the results and I will give some conclusions. So, economical background quite clear. Normally, we have a more or less stable hot metal production and also a stable granulated blast furnace slag production. In Germany, we have a granulation rate of about 90%. But the customer in Germany, mainly the cement industry, of course, has seasonal fluctuations. In wintertime, concreting is not so easy. Moreover, we have sometimes economical fluctuations as we had in 2008-9. And last year in Leuven, I heard the funny recommendation of a professor which said, okay, in the next years we will close all our blast furnaces, so GBS will vanish. So cement producers store your GBS for high value applications for the next years. Very funny, but at the end there is a need to store GBS for weeks, for months, and sometimes for years. The technical background is that we already could show 10 years before that a GBS which is stored in moist condition outside will react, of course. Or you will know the hardening of GBS in a stockpile, and the reason for that is that GBS stored in our lab. Fresh slag, very smooth surface, and the same slag stored as dried material, in that case for more than 5 years, and stored in a moist condition as we received it. What happens? At the surface of the grains you will find a lot of reactive products which are responsible for the hardening. The question now is what happens regarding grindability and reactivity of this slag. If you grind this material as we did it in our lab, comparing the fresh slag and the stored slag, the dried slag and the moist slag, you will see that if we have the same particle size distribution, which means the same fineness of the powder, you will have at the same time very different Blaine values. And the Blaine value is still a parameter often used in cement production. Reality will mean you stop your grinding process if you achieve your certain Blaine value, 4000 Blaine for example. In fact, you will have a coarser material. That's a picture to the surfaces of unground slag, very smooth for fresh slag, and a reacted surface for the moist stored slag. The result is a misinterpretation of fineness. That means the slag, if it is ground GBS, is coarser than normal, than expected. So the feeling is you have a better grindability, but also you have a lower reactivity because, of course, a coarser material is less reactive. Very simple, based on lab scale tests. In close cooperation with Dillinger Hütte, we started then a project because the colleagues said, okay, that's very nice, it's lab scale results, but our customers, our cement industry customers, asked the same question, but regarding technical scale. So we developed a project, and Dillinger Hütte started in 2011 to create a stockpile of 3,000 tons of compacted GBS. We made all chemical, physical and cementitious investigations in our own labs. We formed also CBR test cylinders in order to follow the hardening process. And then from time to time we sampled from this stockpile GBS samples from the bottom and also from the surface from the stockpile. Yeah, we start in January 2011 with creating the stockpile of the GBS, compacting the stockpile in different layers. At the end, that was our test stockpile. From time to time, as I mentioned, we took samples. And the first time it was easy. After 3 months, my colleague was able to do it by hand. After 9 months, it was not so easy. And after 15 months and later on, you can see it was really a problem to get samples from the bottom of the stockpile. At the end, after 55 months, we got unground GBS without any activation, which looks like fresh broken concrete made with slag cement. Nice blue color. The chemical analysis of the fresh and also of the stored slag is a typical one for an European GBS. Not so bad. Basicity 1.4. No special concentrations of main and minor constituents. So a normal GBS. And there's no change, of course, during the storing time. But what changed is, and that's very interesting, the content of chemical bound water and CO2. So not the moisture, chemical bound water in hydration phases. And you see, starting from a low value, during the storing time, the value for water increased to 2.3%. It followed by an increase of the CO2 content because the pre-hydration products carbonate following the time, and therefore also bound CO2 is increasing. If you compare the values of the fresh slag, for example, it's typical twice a year we make a GBS monitoring for the members of FEhS, separately for each GBS from single blast furnaces. Very similar values. And to compare the values after 55 months, we wrote here the data for a GBS which got after 60 years storage outside. And you see the water content is very similar and the CO2 content is much more higher. So we have really the effect of a long storing time in our sample. That is regarding the sample taken from the bottom. The samples taken near the surface have a similar trend, but due to the storing condition, dry, wet, hot, cold and so on, it's not so clear, and the chemical bound water and CO2 is not so high as it is for the main volume of the slag in the inside of the stockpile. Chemistry and glass content, also glass structure, are the important things influencing the reactivity of a GBS, besides technical things like fineness and so on. So let's look to glass content. Glass content, fresh slag and up to 55 months, no change. You cannot find any crystallization products, also not looking to X-ray diffraction. So one basis for reactivity is given also after a long storing time. The average value of our members GBS is around 100% for fresh slag. And also after 60 years we found in another sample 99% glass. Surface reactions. Let's look to the fresh GBS stored at Dillinger Hütte. Sharp edge particles, smooth surface, a certain amount of pores. Normal. After 3 months, you can see surface reaction products, not so dense, but you can recognize them. After 9 months, more and more. And after 55 months, you have a very dense layer of reaction products, very fine products at the surfaces, being responsible for the hardening of the slag. You can see it, that's a scale 1 micron, so a lot of CSH phases in nanoscale, very dense. If we compare such pictures, we choose a very old GBS, the eldest slag which we have stored in our institute, coming from 1912 in France, stored in a dried way, today with very low values and with a very smooth unreacted surface. So it is a moist condition which is responsible for the hydration, of course. To follow the hardening process, we produced CBR test specimen, proctor samples, prepared with unground slag with a certain moisture, protected against water loss outside, and tested from time to time. And that is a sample after 2 years. The values show clearly, or the values follow clearly the hardening process outside, which you could recognize on the pictures in the beginning of the presentation. Grindability. We test the grindability in the Institute with a so-called Zeisel test. It's a small closed ball mill using 30 grams of material, and as a result you will get a curve grinding energy demand kilowatt hours per ton depending on the blane value. And when we measured fresh slags and stored slags, we found that according to the Zeisel test method and according to the blane value, it would be very nice at 4000 blane, which is a typical cementitious fineness. We need only 50% of grinding energy. But looking to the real fineness, to the particle size distribution, we see that that is the starting point, and not the starting point, that is the fresh slag after the Zeisel test. Around 5000 blane. After 3 months, after the same test, we have 400 blane more. But we have at least a very similar particle size distribution. At the end of the storage, we got the same 5000 blane already after 20 minutes grinding instead of 39 minutes, which means is the half. But the material is much more coarser. So according to blane, you save a lot of grinding energy. But according to fineness, you have a coarser material. And therefore, there is no better grindability. The explanation, we made a hypothesis. Prehydration products are located at the surface as we saw. and the main glass volume is unaffected, that we measured. So we think during the grinding process we have a very fast enrichment of the prehydrated surface. Therefore we get very fast, very high blane values, and we see that between blane value and particle size, real fineness, there is an increasing difference. That's a typical prehydration products in nanoscale at the surface. And if you look to the thickness of this layer, it's only about 10 to 20 microns. And the main volume of the GBS grain, as you can see here, is unaffected of any storing conditions. So, what we did, we separated the ground GBS, the GBS which was stored for 55 months. We separated in different fractions, and the smallest sieve which we have is 20 microns. And we analyzed separately chemical bound water and CO2. And, surprise, if you have finer material, the water content, the chemical bound water content is higher, also CO2, and I'm really sure that if we would separate the normally very reactive fraction of GBS below 6 microns, we would find much more higher values. So in the fines, there is an enrichment of the inert prehydrated products. Looking to cementitious properties, we always in the Institute try to adjust a comparable particle size distribution. Also in our project here. That's our starting point, fresh slag, about 4,120 blane. Green curve somewhere in the middle. And here we see the different values for the stored slags. In fact, we have a very similar particle size distribution, but very, very different blane values. But we ignored the blane values. For us, it is important to have the same PSD. The ground material we took and investigated the cementitious properties according to a procedure which was introduced in our institute in 1970 in order to characterize any GBS from somewhere. Today we investigate mixtures 75% GBS, 25% clinker, and since the year 2000 we use really the same clinker which we grind if we need new material. The same sample, 2 tons of clinker which we stored in our institute. We install normally a comparable PSD, which is for a fresh slag about 4,200 blane. We use the same sulfates, the same sulfate concentration. We make also 50-50 mixtures according to the European GGBS standard. In the meantime, we have about 800 samples of industrial GBS coming from all over the world, analyzed according to the same procedure. Also, these samples coming from Delhi. And what you can see here, we made mortar tests according to the European standard, using 75% ground GBS, 25% clinker, and looking to the mortar strength after 2 days, 7 days, 28 days, 91 days. And what you can see here, the lines are the average values, and the individual values are very near around the average. That means there is no loss in strength. There is no less reactivity if you guarantee that you have really a comparable fineness. not a comparable plane value, but a comparable fineness. All results in one table. Glass content not affected. Density is a simple to be measured parameter. Due to the prehydration, you find a decreasing true density of the material. Strongly increasing contents of water and CO2. Very good and easy to measure indicator for the age of a slag. Plane value has nothing to do with the true fineness of the material. Workability of the mortars, in fact, not affected. Strength, we can see maybe a little bit higher early strength, but in any case we do not see a lower strength development. Yeah, let's come to the conclusions. Chemical bound CO2 and water are very good and simple indicators to have a first evaluation of an undrawn GBS coming from somewhere and stored for an unknown time. We see also after years, many years, there are only surface reactions in micron scale. Glass content will be as high as it was during the beginning of the storing. There is no better grindability. And if the PSD is constant, the plane value will increase enormously. But the strength development based on constant fineness will be more or less also constant. Maybe there are some positive nucleation effects. You saw a higher 2 days, a little bit higher 2 days strength. And maybe we have to adjust a little bit the PSD in the finer range, but that's not the most important topic. So again, if you grind stored GBS for cementitious purposes, look to the PSD, don't look to the plane value, and then you will have a reactive slag, which will be so reactive as glass content and chemistry can offer. Additional information you will find in Cement International. The lab scale tests are described already in 2012, and the last industrial results will be presented this year also in Cement International. That's it. Thank you for your attention.
Thank you very much indeed, Andreas, for a really fascinating presentation, and thank you very much indeed for the meticulous work that you've done on separating out the separate effects that you've been examining. That was very, very nice indeed. Thank you. Are there any questions from the floor? Yes, please give us your name and company.
Yes, Mohammed Yassin from UAE, National Cement Factory. In the Gulf, you know, temperature is 50 degrees. So if I go back to your slide.
You go ahead. Thank you.
If I go back to the first two slides, second or third slide, you are doing all your tests on considering storing the slag in moist environment. In our case, when we store the slag, temperature is 45-50 degrees. So we're storing it in a very dry environment. Do you think the end results will be the same if you store it in a very dry environment?
I presume yes, because most of the moisture is not coming from the rain. It's coming from the slag itself. If it is leaving the steel plant, it will have maybe 10%, sometimes more, sometimes less, water content. and the slag is more or less porous. And the water which is in the pores will not come out independent from the conditions in the main part of the stockpile. In the outer part, 20 centimeters, half meter, whatever, there will be a drying, of course, and there will be not such a kind of reaction and not such a hardening. But at the end, the most volume of the slag, I presume, will be show the same behavior as we saw it in that case.
Okay, very quick question on the Slido. Just actually alluding to this slide, why was the storage pile compacted when the pile was formed? Is this actually a normal practice on an industrial scale?
No, it is only to simulate not to have 3,000 tons, but maybe 500,000 tons. That's the only thing. It's only if you have a big storage, which we had in the past sometimes in steel plants, you have not 3,000 tons, but much more and much more higher stockpiles. Therefore, the pressure inside the stockpiles will be higher as you would add only 3,000 tons on a small hill. So it's only to simulate a little bit the real conditions in big stockpiles.
Right, and also just on that topic, you found quite a large difference in hardening effects between the top of the pile and the bottom of the pile.
Yeah.
So the final table that you gave us with the strength development, is that based on samples taken from the bottom of the pile or the top of the pile?
All results are considering only the samples taken from the bottom, because in the outer part you have indeed drying in summertime, sometimes it's raining and so on, so the effect, also the chemical effect, the prehydration effect is much more lower. And therefore we look to the main part, let me say, of the slag, which we took from the bottom.
Right.
Worst case, let me say.
Yeah, I'll give you that.
My name is Zian Wu from the CHC Resource Corporation in Taiwan, and we also done some research about the storing time and the activity index of the slag powder. And we found that because it rains a lot in Taiwan and in some areas, especially in summer, so we found that slag powders, that if we store it outside, and after maybe 1 year, you could see the buttons, the green appearance of the GGBFS. So I think the activity index is gonna drop maybe 20% after you have the green appearance and after maybe 2 years storage. So from your research, you mentioned that even you put longer, more than 2 years, and the sample is from bottom, but the strength didn't decrease as the time goes.
We found it several times in lab scale, in these technical scale tests, and we found it also in practice. We had once a customer which was interested to use a 1 million ton GBS stockpile stored since 1945, unused. And he came to us with samples. We investigated it at the same procedure, and we found the same results. Looking to PSD, looking to chemistry and glass content, we found the same reactivity as we have today for a similar slag regarding the not the best chemistry. And then afterwards they started indeed to use these old heap of GBS. Sometimes later they stopped because the hope to have really 1 million ton of pure GBS was not true. That was another story. But we found every time the same story. We did not find any decrease in strength outside of the statistical range, let me same.
Just to finalise the discussion, I wonder what the total change per particle of granulated blast furnace slag that has reacted over the time. So if you imagine that equate it with the planet, if you like, the amount is equivalent to the atmosphere. It's a tiny, tiny thickness on the surface of the particle, which is less than a 10th or 100th of a percent of the overall particle size. That's unfortunately all the time we have for questions and comment, but I'd like to thank once again Andreas Ehrenberg for his excellent presentation. Thank you very much.
Okay.